The first and most confounding mystery of 3I Atlas is one that seems to defy a basic law of observational astronomy. The dimming paradox has left astronomers scratching their heads in bewildered frustration. This phenomenon is not merely an unexpected variation. It is a direct contradiction of the expected physical relationship between observer and object. Over the past few days of observation, the interstellar visitor has perplexingly lost more than a third of its brightness, a dramatic change that has been precisely measured by instruments across the globe. We have seen its magnitude drop from an initial 10.1 down to 10.6, a seemingly small numerical shift that masks a colossal loss of light. That translates, mathematically, to approximately 63% of its former luminosity, literally vanishing into the void of space, a remarkable rate of decay for an object actively traveling toward us. Here's what makes this observed behavior truly bizarre: the central tension that fractures the conventional understanding of solar system mechanics. The object is still racing relentlessly towards Earth. As these observations were being taken, and the dimming was being measured, 3I Atlas was simultaneously closing the gap between us by a staggering 10 million kilometers. Every single principle of classical celestial mechanics and astronomical observation tells us unequivocally that any object in space must be getting brighter as it approaches the observer, not dimmer, especially when the rate of closure is so rapid. The expectation is not a slow, gentle fade, but a noticeable, incremental increase in intensity as the light source draws nearer. Think about this essential principle using a simple, relatable analogy that grounds this cosmic anomaly in your own daily experience. Imagine a car driving toward you on a long, straight road at night. The simple, unalterable physics of light and distance dictate that its headlights become progressively more intense and brilliant as the vehicle drives toward you, not fainter or less noticeable. Yet 3I Atlas is committing the ultimate astronomical transgression. It is doing the exact opposite of what the laws of distance and light intensity demand. It is fading precisely as the distance shrinks, an act that has pushed the boundaries of natural explanation into the realm of the profoundly unsettling. The initial, conventional explanation that astronomers first tentatively put forth to explain this behavior pointed to its increasing distance from the sun. The logic here is sound on the surface. As any object moves farther away from our star, the quantity of reflected sunlight that makes it visible to us inevitably weakens. If 3I Atlas were a standard, outbound comet that had passed its perihelion, closest point to the sun, and was now retreating into the outer solar system, this dimming would be an expected textbook consequence of physics. But this is where the conventional explanation begins to break down, revealing its inadequacy to fully account for the observed reality. The visitor passed its closest point to the sun weeks ago, a period during which initial fading would be expected. But the crucial point is that the dimming is not gradual. It is accelerating This acceleration of the fade rate, even as the object draws closer to our vantage point, suggests a more profound internal mechanism at work, rather than a simple, predictable response to solar energy flux. The diminishing distance from Earth should be overwhelmingly compensating for the slight increase in distance from the sun, making the acceleration of the fade an active, non-passive phenomenon. This leads us directly to the alternative possibility, one that scientists are quietly and intensely discussing behind closed doors and in private email chains. That internal processes within the object might be at play. The dimming is not merely a passive retreat from the sun's glare, but a consequence of fundamental changes happening within the visitor itself. The most cited candidate for this internal shift involves changes in the nucleus albedo, which is essentially the nucleus's intrinsic ability to reflect sunlight back into space. Imagine a solid surface that is somehow actively altering its reflective properties as it travels through the vacuum of space, like a stealth coating that is activating on a microscopic level. That level of controlled, rapid change is decidedly not typical comet behavior. Most comets fueled by the sublimation of ice become dramatically more active and brighter as they approach the sun, forming expansive comas and brilliant tails, and then they only gradually dim as they retreat into the colder, darker regions of the solar system. The accelerated, unexpected dimming of 3I Atlas, even while remaining one of the brightest objects in our cosmic catalog, holding an improbable fourth place among nearly 100 comets currently under observation, forces us to consider a non-standard, perhaps non-natural mechanism for regulating its luminosity. It's an object that appears to be actively managing its own visibility, a cosmic anomaly that throws the reliability of light and distance into chaotic disarray. Despite this dramatic and confusing fade, the visitor remains a high-profile target for both professional observatories and a dedicated network of sophisticated amateur astronomers. It is these fresh images, captured almost nightly, that are fueling the next wave of intense speculation. These photographs reveal something equally intriguing and structurally complex. The overall tail structure of 3I Atlas appears unusually loose and ragged, displaying dynamic and constantly changing textures that strongly suggest ongoing powerful internal activity rather than a smooth, continuous outgassing process. Professional and amateur astronomers alike are capturing images that document the constant, almost moment-to-moment transformation of the comet's morphology. The structures are not static. They are evolving, twisting, and reforming in real time. Specifically, the images collected from late November paint a fascinating and geometrically impossible picture of this internal energy. Photographs taken in Thailand, utilizing a relatively modest 0.26-meter telescope, a testament to the object's relative brightness, clearly show two prominent, distinct jets of material. Crucially, these images captured the presence of an astonishing anti-tail, a streak of material pointing sunward, directly toward the lower left of the photographic frame. This anti-tail is a particular point of high interest and deep mystery, a phenomenon considered genuinely rare, having been visually seen and documented in only a handful of comets throughout recorded history. Normal comet tails are iconic. They point away from the sun, aggressively pushed by the combined forces of solar radiation pressure and the constant outward flow of the solar wind. An anti-tail, in contrast, is an optical illusion or a highly specific physical effect, often composed of larger, slower-moving particles left behind in the comet's orbital plane. However, the persistence and prominence of this anti-tail in 3I Atlas images is what makes it noteworthy here, suggesting a consistent, non-standard ejection of particles that requires complex orbital mechanics to explain its sunward orientation. Corroborating these findings are Hawaii-based observations from Calopa stars, which captured similar, complex structures with jets of material emanating, not in a single, predictable plume, but in multiple, seemingly arbitrary directions. Each new, detailed image tells the same provocative story. This is demonstrably not a simple, passive object, a dead, icy rock drifting slowly and predictably through space. It is actively and powerfully expelling material in structured, coordinated patterns that hint at a controlled expulsion mechanism beneath the surface. The question that pierces the core of the natural explanation is, why would a natural, kilometer-sized comet, an object born of ice and gravity, behave in such a structured, almost deliberate way, maintaining these bizarre orientations and erratic structures? The ragged, loose structure of the main tail further intensifies these structural questions. Instead of the anticipated smooth, uniform stream of particles that one would expect from continuous sublimation, the tail appears to have discrete structures, observable clumps, distinct arcs, and gaps that strongly suggest episodic, rather than continuous, ejection events. The material is not flowing smoothly and continuously. It is being released in sudden, powerful bursts. This suggests a pattern where each rotation, each asterisk 16.16-hour cycle asterisk, a number we will return to with intensity, brings another pulse, another forceful injection of fresh material into the tail. Over time, this rhythmically segmented ejection process creates the irregular, non-uniform structure we observe, a tail that is less a graceful stream and more a series of smoke rings pushed out into space. It is worth pausing to recognize the vital role of dedicated amateur astronomers in this unfolding narrative. The images they are capturing with relatively modest equipment, such as the quarter-meter telescope used in Thailand, can and often do reveal fine details that massive, professional surveys might inadvertently miss due to their limited fields of view or the need for quick broad sweeps. These dedicated observers are watching 3-eye atlas night after night, providing the continuous real-time monitoring that large observatories, hampered by competitive scheduling and limited observing windows, simply cannot match. The images they're producing consistently show a dynamic, rapidly changing object, utterly refusing to behave as a static comet, following a predictable gravitational path. This community of skywatchers is forcing professional astronomy to pay rapt attention, using the sheer volume and continuity of their data to challenge the institutional view of what this object can be. The structural oddities of the tail lead inexorably to the most compelling and mathematically troublesome revelation. The light from 3 Atlas has been pulsating with remarkable, unvarying precision since its initial discovery on July 1st. The measured period of this rhythmic variation is exactly asterisk 16.16 hours asterisk, a level of stability and accuracy that immediately raises profound questions about the internal mechanisms of a natural object. This pulsation displays variability reaching amplitudes of tens of % of the total light output, a significant and easily detectable change in total brightness. Initial reports, seeking to fit the new data into old models, attributed this pulsation to the rotation of an ellipsoidal nucleus, the classic potato-shaped core, tumbling through space. The idea was simple, elegant, and entirely plausible. As the non-spherical nucleus rotates, the amount of reflective surface area facing the Earth changes, causing the reflected light to brighten and dim periodically. That explanation seemed reasonable on its face, fitting the general framework of cometary physics, until the Hubble Space Telescope took a closer, definitive look at the nucleus itself. The Hubble observation, conducted on July 21st, changed everything we thought we knew about the object's light source, dismantling the elegant rotational hypothesis in a single devastating stroke. The data revealed a shocking truth. Most of the light detected from 3-eye Atlas doesn't come from the small, solid nucleus at all. Instead, it originates from a gigantic glowing halo, a transparent coma of gas and dust that surrounds the object's core. While you can dimly perceive the nucleus through this transparent halo, it accounts for only a tiny, minuscule fraction of the total light we receive. The brightest pixel in the Hubble image, the one that presumably contains the nucleus and its immediate surroundings, represents just a small percentage of the overall light output from the entire system. Let us delve into the mathematics of why this detail is an insurmountable problem for the rotation hypothesis. If we were to naively assume that the light came from the solid nucleus surface, the simple physics of albedo and distance would require the object to have an effective radius between 10 and 23 kilometers, depending on the specific wavelength of light observed. But that assumption is mathematically impossible. The actual radius of the nucleus is much, much smaller, likely around the 2.8 kilometer mark, based on upper limits meticulously derived from the high-resolution Hubble data. At that small size, the solid nucleus core reflects less than 1% of the total measured light So here is the unavoidable, paralyzing problem that has divided the astronomical community. If the spinning nucleus core contributes less than 1%, 1% of the total light we see. How can its rotation possibly cause a 10 to 30%, tens of percent, variability in the total observed brightness? The simple, unyielding truth is, it cannot asterisk. The mathematics doesn't just get strained. It completely collapses. It is like saying the tiny blink of a flashlight inside a massive football stadium is responsible for the overall fluctuation of the entire stadium's lighting system. This fundamental mathematical conflict definitively proves that the 16.16-hour pulsation isn't coming from the nucleus rotation. It's not a function of passive geometry. The pulsation is coming from something else entirely, something that actively and profoundly controls the rate at which the light-scattering coma brightens and dims. This realization shifts the focus from a passive, geometric process to an active, controlled, internal one. The rhythm is real, the numbers are locked, but the source of the oscillation remains elusive, forcing us to consider processes that go far beyond the conventional ice ball tumbling through space. The failure of the rotation hypothesis leads us directly to the heartbeat hypothesis, a scenario which seeks to explain the rhythm through an active process rather than a passive one. Over the past month, multiple columnated jets of material have been consistently observed emanating from 3I Atlas. The key observation here is that these are not just random, sporadic outgassing events typical of a chaotic comet. They appear structured, coordinated, and in a word, deliberate. The hypothesis posits that if the mass loss in these powerful jets pulses periodically, that is, if the jet turns on and off on a specific cycle, the resulting coma of scattered gas and dust would inevitably display a corresponding periodic variability in the amount of reflected sunlight. Think of it like a truly massive cosmic lighthouse, but instead of rotating beams of focused light, we are seeing rhythmic, controlled pulses of gas and dust injected into the surrounding space. The light we observe is the sunlight scattering off this freshly ejected material, and the precision of the pulse dictates the precision of the light fluctuation. The central question becomes, what is the fundamental mechanism that is driving this perfect, unvarying rhythm? For a natural comet, the explanation that has gained the most traction involves a localized, sunward Jetta-specific anti-tail feature that activates only when a large, isolated pocket of highly volatile ice on one side of the nucleus rotates to face the direct solar radiation. As the nucleus rotates on its axis, this volatile ice pocket alternately faces toward and then away from our star. When it faces the sun, the intense solar radiation rapidly and powerfully sublimates the ice, forcefully releasing gas and dust in a concentrated, powerful jet. The coma gets pumped up instantaneously with fresh, highly reflective material, causing the object to brighten. When the pocket rotates away from the sun, the activity naturally decreases and the coma begins to dim. This creates the observed heartbeat pattern, a regular, powerful pulse of material expelled exactly every 16.16 hours as the nucleus completes one full, precise rotation. The numbers, initially, support the physical feasibility of this scenario. Assuming an outflow velocity of 440 meters per second, a measurement derived from meticulous James Webb Space Telescope data, the sublimated volatiles can travel approximately 25,600 kilometers during one single 16-hour rotation period. That is a substantial, massive distance, entirely sufficient to create a sizable, bright coma that would significantly affect the object's total brightness, fully accounting for the observed amplitude of the pulsation. The heartbeat analogy is thus apt. Each pulse sends a stream of material through the coma, much like a powerful surge of blood pumping through an artery, rhythmically refreshing and brightening the immense halo around the tiny nucleus. But here is where things once again start to get strange, where the scientific narrative hits an abrupt, puzzling wall. This beautifully described, self-consistent heartbeat pattern should be clearly and easily visible in a series of well-calibrated, high-resolution images taken over several consecutive days. Astronomers should be able to create a definitive, high-impact movie, a time-lapse visualization showing the coma brighten and then dim in perfect, unyielding sync with the 16.16-hour period. They should literally be able to watch the columnated jets pulse powerfully on and then quietly off, like a cosmic metronome, keeping a perfect time we never knew existed. Yet, despite the critical nature of this evidence, no systematic, detailed study of this phenomenon has been officially published in the scientific literature. No major research team has presented a comprehensive, high-quality movie showing the periodic brightening and fading. This absence of crucial empirical data is not merely an oversight. It's a profound vacuum in the investigation. The essential question is, why not? Is it because the pattern, upon meticulous photographic investigation, simply does not fit the expectations of a naturally sun-driven rhythm? Or is it a far simpler, yet equally troubling possibility, that no one has yet devoted the necessary, continuous telescope time to look carefully and systematically enough, hampered by the competitive pressures of large observatory scheduling? The missing movie is, itself, a clue, a sign that the observed facts may resist the neat, natural explanation we are so desperate to impose upon them. The logical chasm created by the missing empirical evidence, the systematic time-lapse of the pulsing jet, is the void into which the most intriguing, and perhaps most uncomfortable, possibility has begun to creep. The idea of an technological object **. The shift in focus from passive geometry, the nucleus shape, to active processes, jets, is the distinction that fundamentally matters, because it allows for a discussion of *choice* and *control*. Something is actively driving these jets, and something is precisely maintaining this flawless, unvarying rhythm. For a technological object, the physics of the jet's direction and timing are radically liberated from the constraints of solar heating. The direction of a pulsing jet on an artificial craft becomes entirely arbitrary, not necessarily pointing toward the sun, as a rotating ice pocket requires. A sophisticated internal propulsion system, a controlled venting mechanism, or even a system for trajectory adjustment wouldn't need to follow the constraints of solar physics. It could orient itself in any direction, maintaining thrust or releasing material according to a pre-programmed internal schedule entirely decoupled from its orientation relative to the sun. A definitive, systematic time-lapse movie showing the periodic brightening of the jets around 3I Atlas over several days would be the ultimate test to reveal the truth. If the jets consistently orient themselves toward the sun, precisely following the predictable solar heating pattern, that would overwhelmingly support the natural comet hypothesis, neatly closing the case. But if the jets pulse in different, non-aligned directions, or if they maintain orientations that do not directly correlate with the sun's position, that observation becomes monumentally harder to explain naturally. It would suggest an object that is choosing when and where to vent material, rather than passively responding to a hot star. This kind of rapid, non-correlated structural change, as reported by observers like Bobby Howe at Calopa Stars, who captured images showing a reconfiguration of the emission patterns within a single 24-hour period, strongly leans toward an active, managed system. This structural mystery dovetails uncomfortably with the subject that has yet to make its way into formal scientific papers, but is already the subject of intense private speculation: the radio observations. Harvard astronomer Avi Loeb, who famously investigated the first interstellar visitor, Oumuamua, raised this critical question in late November. If the jets are pulsing with such perfect precision, could this coordination extend to electromagnetic emissions? Natural comets do indeed produce faint radio waves, usually when their ionized tails interact frictionally with the solar wind, creating a broadband noise. If this synchronization were confirmed, it would mean that three completely different types of physical phenomena, the optical variability, light, the kinetic pulsation, material jets, and the electromagnetic emissions, radio, are all locked to the same singular clock. That level of internal coordination is technically not impossible naturally, but it would require an astonishing, almost unbelievable level of homogeneity and coordination within the comet's structure and thermal dynamics that we have literally never encountered before. It is a level of organization that is infinitely easier to explain as a product of design rather than as an outcome of natural, chaotic processes. This is the point where some researchers, quietly and away from the glare of public scrutiny, have suggested the obvious, albeit sensational, possibility. What if we are witnessing deliberate, active behavior? Not the random outgassing of an ice pocket, but controlled venting a technological object managing internal pressure, adjusting its trajectory for a reason we cannot yet fathom, or, most provocatively, even signaling a precise internal state. It sounds like the plot of a science fiction movie, and maybe it is the ultimate case of pareidolia. But when you begin to systematically eliminate the impossible explanations, the rotation hypothesis, the simple distance fading, whatever remains, however improbable it may sound, demands serious, immediate consideration. The entire conversation about 3I Atlas now pivots on a single urgent point, the fate of the next 2 weeks. The main intrigue of the coming weeks centers on the critical decision of whether NASA will deploy the full combined might of the Hubble Space Telescope HST, and the James Webb Space Telescope JWST, for a fresh set of observations. Both instruments have previously captured images of 3I Atlas, but those occurred when the object was much farther from the Sun, limiting the resolution and detail possible. The current, rapidly approaching orbital configuration is unique and geometrically perfect. It allows both of the world's premier space telescopes to safely point at the visitor for a fleeting window of the next 2 to 3 weeks without risking any damage from solar proximity. This is a narrow, non-repeating window of opportunity that will not come again under these conditions. The stakes are immense, and the question is simply, will they take it? NASA has maintained a position of conspicuous, unnerving silence on this matter. There have been no official public announcements, no confirmed observing schedules leaked, and no public comments from agency spokespersons regarding an immediate observation campaign. That silence, in itself, is highly interesting. These are the most powerful scientific instruments ever built by humanity, capable of resolving details that ground-based instruments, however advanced, cannot match. The scientific value of observing an interstellar visitor at this proximity and activity level is enormous. A generational data capture. Consider the potential. Webb's unparalleled infrared capabilities could penetrate the transparent coma, providing an unprecedented analysis of the jet's composition, definitively answering questions about the specific volatiles, water, CO2, etc., that fuel them. Hubble's high-resolution imaging could meticulously track the structural changes in the nucleus and the surrounding material hour by hour, providing the missing movie that could confirm or debunk the heartbeat hypothesis. The combined data would be the definitive answer key to this cosmic puzzle. So, why the hesitation? Why the deafening silence from the agencies? Perhaps there are genuine scheduling conflicts with other high-priority, time-critical targets. Perhaps there is a legitimate institutional concern about public reaction if the observations reveal something truly unprecedented, a fear of the ET headline dominating the scientific narrative. Or, the most optimistic possibility, perhaps the observations are already secretly scheduled, with the results being meticulously filtered and held quiet until a definitive paper is ready to be published, avoiding sensationalism. The astronomy community is intensely divided. Some respected researchers are pushing hard, arguing for immediate observation, while the opportunity is geometrically perfect and the object is bright enough. Others, more cautious, counsel patience, suggesting that the object will remain observable from Earth for months to come. But on one thing, everyone from the most radical theorist to the most cautious observer agrees. This chance to observe an active, highly organized interstellar visitor at such close range with our best, most capable instruments should not be wasted regardless of the conclusion it leads to. The urgency is further compounded by the dimming paradox itself. The brightness decrease complicates the scheduling decision immensely. If 3I Atlas continues fading at its current, accelerating rate, it may rapidly become too faint for detailed, meaningful spectroscopic analysis within a matter of mere weeks. The window isn't just about orbital geometry and safety. It's critically about having enough *** photons to work with ***. Fainter objects necessitate exponentially longer exposure times, which severely limits the number of observations that can be performed and restricts the depth of the spectroscopic analysis that could definitively determine its composition. A clock is ticking not in months, but in the rapid, irreversible cycle of the next few weeks. The balance between waiting for hypothetically ideal conditions and acting before the unique opportunity irrevocably vanishes is tipping heavily toward urgency. Every day that passes without a confirmed JWST or Hubble observation is data we will never recover. A loss that could haunt the field of interstellar object study for decades to come. The sheer novelty of 3I Atlas' behavior forces us to contextualize it against the only 2 interstellar visitors we have ever previously detected. This is only the 3rd interstellar object ever confirmed passing through our solar system. The first, in 2017, was **Oumuamua***, the strange, cigar-shaped object that famously accelerated away from the Sun in ways that the gravity of our star alone couldn't possibly explain, a departure that hinted at non-gravitational propulsion. Crucially, Oumuamua vanished before we could capture good, detailed data, leaving us with a tantalizing, unanswerable mystery. The second was Comet Borisov in 2019, which appeared more conventionally comet-like, fitting neatly into the established models, albeit with an interstellar origin. Now we have 3I Atlas, a visitor that seems to occupy an unsettling middle ground between the two, yet possessing unique, internally coordinated features all its own. Its interstellar origin is definitively confirmed through rigorous orbital analysis. Its hyperbolic trajectory means the object is moving far too fast to be gravitationally bound to our Sun, a definitive signature that it originated from beyond our solar system, perhaps traveling for millions or even billions of years before its brief, active visit to our neighborhood. During that unimaginably long journey, it experienced a radiation environment between the stars, temperatures approaching absolute zero, and impacts from high-velocity interstellar dust grains. Yet, despite that harsh, brutal voyage, it arrived in our solar system capable of producing bright, highly structured, and coordinated jets. The volatile ice reservoirs that fuel these jets survived intact. The nucleus maintained its structural integrity without fragmentation. Whatever this object is, it is remarkably, almost unnaturally, robust. Natural comets from the Oort cloud, the distant icy repository that surrounds our solar system, often fragment or disintegrate spectacularly when approaching the Sun for the very first time, torn apart by thermal stress and tidal forces. 3I Atlas shows absolutely no signs of fragmentation. It is holding together, maintaining organized outgassing patterns, and continuing to function in ways that suggest either exceptional durability, born of alien geology, or something far more orchestrated. Remember the lesson of Oumuamua. We missed our chance with that one. 3I Atlas is different. We've had months to observe it, but instead of finding definitive answers, we have only accumulated more confounding questions. This brings us to the 3 crucial tests that could definitively settle the debate in the next 2 weeks. Tests that require the immediate deployment of our most powerful instruments. The rhythm test. Does that 16.16-hour rhythm remain absolutely, perfectly constant? Or does it finally drift, however slightly, as the laws of chaotic natural rotation and mass loss dictate it should? 5 months of clockwork precision is already pushing the boundaries of what we'd expect from a chaotic ice ball. The geometry test. Do the jets keep pointing in directions that make perfect, logical sense for sunward heating? Or are they observed firing wherever the object internally dictates, in violation of the solar heating model? A systematic, continuous time-lapse of the jet structure is the only tool that can provide an immediate and irrefutable answer. The synchronization test. The big one-coordinated radio telescope observations. If simultaneous electromagnetic emissions are confirmed to be pulsing in sync with the kinetic and optical phenomena, that is a level of unified, self-maintained organization we have simply never, ever seen in nature. All the tools needed to perform these 3 definitive tests exist. The object is right there, entering its peak viewing window. We just need a coordinated, focused effort to point the telescopes and collect the irreplaceable data before the window closes forever. The debate in conference rooms and email threads is exploding with intensity. Some astronomers are rightfully calling this the single most important observation opportunity in a generation, a chance to define a new class of objects. Others urge deep caution, warning against the media frenzy that accompanies every mention of the technological possibility. But the one thing on which no one is debating is the raw, undeniable fact. Asterisk, asterisk. We are watching something that does not fit our current, accepted models. Whether that means our models need a drastic overhaul, or whether we are witnessing something genuinely unprecedented and artificial, that is the question that sits at the core of this cosmic mystery.